Okay, so today we're gonna have Sui to introduce the operator learning by wavelets. This is something when we discuss about Fourier operators, actually having some kind of discussion, right? So how about use wavelet transform? And then someone has done that, and then shows pretty good performance. And then after that, we'll have Tushar to introduce the recent operator learning by transformers. Sui, you can go ahead.
Okay, so today I'm going to introduce a paper. They use wavelet transform to make a better performance than Fourier neural operator. So I'm going to.
When is this paper? When was this paper published?
2021 or 2022. I don't remember.
Paper, right?
Yep.
Okay.
And I'm going to introduce the problem they are aiming to solve, and talk about the difference between the wavelet transform and Fourier transforms, and introduce it from math perspective and from code perspective, and introduce the evaluations of it and do a small conclusion. So the problem they are aiming to solve is the integral over there. Basically, in every homogeneous differential equation, we can turn them to this form, and the t over there is the differential operator, and the a is our input, and the hardest part is the integral. So in Fourier neural operator, they develop a way to impose the integral to the convolution form, so that they can use the Fourier transfer to transfer the kernel matrix to Fourier space, and the input to Fourier space as well, do the multiplication and transfer them back to get our result. And in this paper, they do the similar things, but in a wavelet subspace. They will transform the kernel matrix to wavelet subspace, and the input to wavelet subspace as well, and do the multiplication and transfer it back.
Okay, so I guess you need to be more explicit in that. So in Fourier neural operator, this guy is computed using the convolution theorem, right? So you're gonna first do a Fourier transform over K. Then you multiply with Fourier transform with your input function A, right?
Yep.
Then you do the inverse Fourier transform, right?
Yes.
This is actually the same as this convolution. So in the wavelet transform, they have a similar convolution theorem, like you replace f and the inverse f by wavelet transform and inverse wavelet transform. The result still consistent.
The result of wavelet compare with who? Fourier or
transform. We know that from the convolution theorem, we know that, okay, if you want to do a convolution of your input function A with respect to this kernel K, it is equivalent to first doing Fourier transform over K and do Fourier transform over A, multiply them in the frequency space and do the inverse Fourier transform. They're the same. But if we do the wavelet transform, do we have the same theory? Like I do.
Here I just want to compare the similarity between them, but actually the step are totally different between them. I mean, yeah, they transform the input and kernel matrix to wavelet subspace, but the wavelet transform have different dimension output. I will introduce in here just like the output over here from Fourier. They have 1D output, only frequency, but in the wavelet transform they have 2D. So we cannot do the simple multiplication as Fourier transfer does.
They have the way to show the equivalence, right? You do the wavelet transform in the wavelet space. You, I don't know, you're doing some operations over the transform K and transform A, and then you do some inverse transform. You're gonna be equivalent to this TAX, right? The original definition.
Yes, it's a T is the operator over there, and in a fast wavelet algorithm, in the textbook they mentioned how to transform the T to the wavelet subspace and how to transform the input to the subspace as well. Yeah, the flow is different from the Fourier transform, but the roughly concept are similar.
Okay.
I have another question about the slide. So in the FNO, they assume that the K is a stationary kernel. So for wavelet transform, is the same assumption still hold, or K can be non-stationary kernels, since we don't need to do the Fourier transform and evolve the convolutional theory.
What does that mean? Stationary kernel, the constant, or
so if you do the full Fourier transform, so there is a general form of this integration in the neural operator. Only the K is a stationary kernel. You can do the Fourier transform. And then never mind. It's just a question. Never mind.
Okay, but I can mention, but I will mention that later, but I can mention here as well. They implement the kernel matrix over there by neural network, the same one as the Fourier neural operator.
Yeah. I'm just curious about their motivation. Why they replace the Fourier transform with wavelet transform? Yeah, because if you read, you can look at the journal paper of the neural operator. They have so originally there is a very complex form of the kernel function, but they simplified it as a stationary kernel, so you can use the Fourier transform. If this is it's not a stationary kernel, you cannot use the Fourier transform. Never mind, just curious. Yeah.
I think the biggest difference is that they don't have to bring the kernel matrix from the original space, there's subspace or Fourier space. They don't have to do that, no matter in Fourier transform or wavelet transform. The only thing they need to do is to bring the kernel matrix from a Fourier space to the original space, or from a wavelet subspace to the original space. That is the only thing they need to do.
Okay.
Yeah. So I'm going to talk about the difference between the Fourier transform and the wavelet transform. So in Fourier transform, we will put the signal into a transform and get our output, the frequency. And basically, there is some sacrifice. So after the transform, we get the frequency information from the Fourier transform, but we cannot know the time. I mean, we cannot know the exact when does the exact frequency happens in the original data. That's the reason why wavelet transform develop. So basically, it's not means wavelet transform is better than Fourier, because in a signal process, it's a trade-off between the time and frequency. We can just see the results over there. Over here. So here's the result, and we can get the time and the frequency as well. But as we can see, compared with Fourier transform, in every time tick, we can only roughly know what's the frequencies consists of the signal, but we cannot know detail about. We cannot know as clear as a Fourier transform. We cannot know is there 2 hertz or 1 hertz in there, or how much amplitude among the region. It's unclear. Yeah, so people present another way to make it clear, but no matter how much people do, they cannot get as clear as Fourier transform. So that's a trade-off.
Oh, so you mean, if you do Fourier transform, you got some global characterization of the frequency, right? It's a distribution of the frequency, but you want to know, like, if I zoom in some small period of time, what are the frequency distribution over that time range? This is what's the motivation of the wavelet.
Can you repeat? You mean they can get the time information and what?
Yeah, I'm just want to clarify about your motivation. You said that if we do Fourier transform just tell you the frequency function, right? So frequency function is global. It's just telling you, okay, for this whole time signal, what's the distribution of frequency? What is their power or amplitude of those frequencies, right? And what's the benefit of wavelet? So wavelet can tell you at a specific time, I mean, some small region surrounding that time, you know, the corresponding frequency distribution. This is what wavelet tell you.
Yeah, but not the frequency information is not as clear as Fourier transform.
Okay, why is it not as clear as Fourier transform?
We can only know to roughly the range. Like Fourier transform, we can know the first frequency is in Fourier transform, we get the data from the low frequency to the high frequency. And we can know exactly what hertz, the number of the hertz in after Fourier transform. But in the wavelet transform, we cannot know exactly. We can only roughly know the frequency number, but not as clear as Fourier transform. That's why people need a special method to get as clear as much to meet the same effect as the Fourier transform, but cannot. It's a trade-off.
Yeah, maybe. Yeah. Go ahead, Shibo.
Yeah, so the frequency A here is not a true frequency. It's like a parameter of the basic function, right? So
what's parameter?
The A is this one. This is not a. So by decompose the function into. I'm not very familiar with the wavelet, but is it decomposed the summation of the basic function?
Yeah, I will explain what does it do or how does it work in concept.
So each basic function looks like the below figure.
What figure?
So yeah, what's the basic function looks like?
So sorry, I didn't catch up the question.
What she was asking is that what does this look? What does the psi function looks like? It looks like,
yeah.
Right?
Oh. Basically, it can be any form as long as
it can be any form. Okay.
it meets certain condition. And I remember there are 3, but I can only memorize 2. So the first is the integral of this function have to be 0, which means they have like a mirror. The positive quantity have to equal to a negative quantity, like sine and cosine function as well. And the second condition is the square side to the integral has to be 1. This is the second condition. They have to, as long as they meet a certain condition, yeah, they can be the wavelet.
So the frequency here, A is here, does not reflect the true frequency of the original function. It just reflects the what's the psi function looks like. If you get the character function frequency characteristic of the psi function, you have to FFT do the Fourier transform of the psi function.
I think it's probably different from Fourier. Okay, so we have the wavelet over there, and the A is the hyperparameter which adjust the wavelet, and the B as well. So by adjust A, we can expand or shrink the wavelet, and by adjust B, we can shift the wavelet in any time tick. So that is what A and B do in the wavelet. And how do we do the transform? So basically, we will use the wavelet to do the inner product, to do the projection with our signal data, to see how much similarity they are. I mean, to see how much the same from the wavelet data and the original data, and by adjust the A and B to get the frequency and at any time tick. So that is the main works. That is the main method how to do the wavelet transform.
Okay. So then how to choose the psi function, the basis function? So if it's a prior knowledge. So if I have a smooth function, then I think I use some cosine function or sine function is better. Or if I have a very rough signal, maybe I use some square basis function is better. So is that a prior knowledge?
This paper doesn't mention how do they pick the wavelet.
Okay.
They didn't mention. Yeah, and I think it's just like the distribution. So like we have many distribution, Gaussian and Dirichlet, lots of distribution, and we cannot say which distribution is more general or is better in any case.
So thank you. We'll catch up the wavelet later.
Well, wavelet is a family, so there are lots of different waves in the family.
Yeah.
Okay, so overall, after we do the comparison to the inner product, we can get the result like that. So the original input data, we can tell the signal, the white line, goes from the low frequency to a high frequency. So from a result, we can know the same trend from it. By time, the frequency goes from low to high. So I think that is the trend is the part that Fourier transform cannot show to us, show to people. That's it. So next, I'm going to talk about talk from the math perspective. So the goal is to solve this problem, and from a fast wavelet transform, they mentioned we can transform our operator from the original space to the subspace N by this equation. The Q over there is the wavelet, and the P over there is a projection projection can project the operator from the original space to the wavelet subspace. And in this paper, they not only in this paper, in the textbook, they also put those items to the alphabet and use the as I mentioned in the beginning, the wavelet transform is similar to Fourier transform because they transform to the subspace and do the multiplication and transmit back, right? So in here, they will transform the operator to the subspace and do the same thing to the input from the original space to the subspace. And here, they will do the multiplication. Is a little bit more complex than Fourier transfer. Do the multiplication and transfer it back. Overall, the flow is similar, but the content of the step are different and more complex.
So what does QI? What does QI mean? What is QI?
The Q here from the textbook, they said it's a wavelet. The wavelet signal.
Function?
What?
Is a psi function?
I guess so, because this paper they didn't do too much math on each item. They just use neural network present each item. They didn't calculate the Q, didn't calculate the P. They just use neural network to get a result.
Yeah, but you need to figure out what's the meaning of this, right? What is P? You said it's projection. It's a matrix or it's a function? What does P mean?
I guess it's a matrix. I guess just used to transform the T to the variant of T in a subspace, I guess.
But what does T mean? If you PL, QL are matrices, and then T here is matrix as well, but T is operator. So what's the T here? Is a function or is a matrix?
In this paper, they didn't mention too much about this equation because I think because this is the part hard to compute. And I have to mention they don't have to do this part. Actually, as a Fourier transfer, we don't have to do this part because we already assume the A, B, C, T over there already in the subspace. As I mentioned, we have to calculate the integral. We only need to bring the input to the subspace, to the wavelet subspace. We don't have to bring this to subspace. We start compute this one in subspace. We don't have to bring it to the subspace. We don't have to do that.
Yeah, but at least you need conceptually tell us what's the procedure, right? What's the computation procedure? What's the usage of Tn here?
The Tn here is an operator, but in wavelet subspace. The T here is an operator, but in the original space. That's the difference between them. And how to transform it from the equation is here. And in this paper, they don't need to do the computation over there. They directly
So the t in the Tn, or so the t in the Tn formulation is not the t in the integral.
The Tn is the t, but in the wavelet subspace. The n means the subspace.
Yeah, but if you are saying that, so it is the operator in the wavelet space, it means that, so it seems like the weight matrix, the Fourier coefficients in the Fourier space, right? So it is
They are in wavelet subspace, not in Fourier subspace.
Yeah. I'm trying to make a connection or understanding about what is the t here. So, but the t in the integral is the operator. So we don't need to know the operator. Basically, the TAX is the U, right? So we don't know this one. But the T in the formulation seems like you're saying that it's an operator in the wavelet space. So in the Fourier space, we do the linear operation. So basically, you just multiply the Fourier coefficients with the weights. So I guess then T is serve the similar role. So T needs to be learned, right?
Yes.
Coefficient. Okay.
In this paper, they just use a neural network to get the result of the I-chain, QGQ, QGP, and so on. They just use 4 different neural networks to present the I-chain.
So what's the input to the neural network?
They put the A into they put the output from the A to the neural network. So overall, the step we have to do 3 steps to transfer the T to subspace Tn, to transpose to transform our input to wavelet subspace and do the multiplication and inverse back. We have 3 problems here: how to calculate this, how to calculate this, and how to calculate this. In this one, they used neural network to present the operator of there, and in here, they have to bring the input to the subspace. So we will mention that later. And in the inverse, we will mention that as well. So in the neural network, their input is to put the output SND of there into it. That's it. That is the input.
So what you mean the input of the neural network is a function, continuous functions?
You mean the A, B, C, and G is a continuous function, or?
I mean the input of the neural network.
I think it's discrete data.
It is a function, right? AX. MWT-AX. So it is a continuous function or discrete function?
Oh, you mean an MWT is multi-wavelet transform.
Oh, okay.
So it's wavelet transform, and due to our data is discrete, so in practical, the function should be calculated in discrete as well.
Okay, gotcha. So it's a discrete data. Okay.
Discrete data, so the function can only calculate by discrete way. Okay.
Why not you just tell us the computing procedure?
Okay. So in the wavelet transform, they only need to do one thing: decompose. And how to do that? The first, they have to transform the input data to the wavelet subspace and multiply with a filter over there to get the next subspace. It's kind of the flow over there. We have the wavelet, and we will do the projection at the beginning and do some adjustment to the A and T and do the projection again and adjust it A and B again and do the projection again. That's why we can get the result of there. And in the decompose, they do the similar things. They will after they transform from the original space to the wavelet subspace at the beginning, they will multiply it with the filter again to get a result and do it again to get another result. Every time.
What does S and D mean?
The S and D corresponding to the A and B over there.
But you need to choose a set of bases, right? You have to pre-choose a set of bases, or just you specify the form of psi.
What do you mean choose the specify?
I mean to do the Wavelet transform.
Hmm.
What you need to do is you need to give the form of the psi. That's it. And then the decompose will just iteratively compute this SLN and DLN.
Let me repeat your words. So you means we only multiplied with the H and G over there.
No. I mean conceptually, what are you going to do to finish the full Wavelet transform? You're gonna first give a form of the psi, right? In your previous slide.
Mm-hmm.
Then what's the subsequent steps? Suppose I give the form of my psi, which could be a Gaussian function. Then what's the next step? What's the procedure? Where do you get H0, H1, G0, and G1?
Yeah, I have the same question.
We'll have more detail later, and I will explain every item. In this part, I only want to, yeah.
I have a question, another question about following Dr. Zhe's question. So if I have a function, so is the wavelet decomposition is decomposed into just a summation of a psi function, or there is a coefficient in front of each psi function. So if there is no coefficient, we need to determine each A and B in the psi function, right? So it's to learn the coefficients on fixed basis, or learn the parameters of the basis functions.
I think we don't need to bother A and B, how to learn A and B over there, because they will set the minimum unit to the A and B over there. Like in this part, the L means the time tick. So they will select the data by 2. And I think they will just filter the data. Pretend we have the data from 0 to 10, and after this filter, they only get the 0, 2, 4, 6 until 10.
So it still needs, for the wavelet transform it still learns the excuse me, learn the coefficient on a fixed basis, not the dynamic changes basis.
from the paper is no, they fix the.
They fixed the AB. So prior,
They fix the minimal unit. Yes.
So before
every
I
time,
run the wavelet, so I know I have a set of A and B. I know what the basis function looks like. I just don't know the I just don't know what's the H and G looks like. I just determine the H and G in an iterative manner, right?
So let's pretend out as a filter, and I'm going to say it's a constant actually, and later we will talk about how to compute it. So we got a filter, and the only thing we need to do to decompose is to multiply our input in the wavelet subspace with the filter, and to get the data after the filter. Okay. So how do we calculate every item? How do we transfer from the AX to the S? How do we calculate the H, G, and sigma there? So in this paper, there are many maths. So first we have to introduce about the wavelet we mentioned. In this paper, they present a wavelet by polynomial set. And what is polynomial set? So polynomial set actually is a family, just like wavelet, wave. They are all families, and here is one of the member in the family from Wikipedia. So phi here is the variant from the polynomial functions, and the things we need to do to transfer our input AX, the F here, to the S is to do the inner product together. The K here means N, that means how much order we want to build or we want to project, how much detailed information we want by the polynomial set. That's it. The K means how much high degree, how much high order in the polynomial set. So after the inner product, we can transform our input data from the original space to the wavelet subspace N. And
the definition of psi.
Yeah. And the psi, yeah, we can do the same thing by psi to get the D. How do we get to the psi? The psi over there is in the space the same as the wavelet, and here they mentioned a method to calculate the psi. The method is Grace-Smith method. So there's a rule: the phi and psi have to be orthogonal. So how do we calculate the psi from phi, which is orthogonal to each other, by Grace-Smith method?
Okay, so they pick up phi to be this square root of 2i plus 1 times some polynomial, right? That's your definition of phi. Then you got phi n GL. Then you got psi GLN. Then you got SLN and DLN. They are just projection.
Yep. Exactly.
Projection on mu n, what does it mean?
Which part?
The inner product. The inner product between F and then phi Ln. And on mu n, what does it mean? It's an integral.
It's a measurement. It's a measurement. And that is one of the reasons why we cannot just we are hard to calculate the inner product. The mu n is an integral, and it's a nonlinear integral.
My understanding that this one
not integral, sorry. mistake. The measurement.
This should be some f, right? Fx times phi n j l x and d mu
Yeah.
n, right?
Yeah, exactly. The measurement.
But what's the choice of mu n? What's the definition of mu n? Oh, this is the general. This is just the general definition. So
I
mu n
didn't see two.
measure.
Uh-huh.
Yeah, I believe it varies along with n, right? So different steps, and you're gonna have a different measure.
Yeah. Yes. So what is the problem, or what's the questions?
My question is that how do you define mu n? How does it relate to the Waverly transform?
I'm not sure I didn't see too much part how do they do the transform, but I see the similar things in here. So to calculate the edge, we have to figure out the integral over there, and the original form from the integral actually look like this one. The u is a measurement as well, so they cannot do the integral there, and they mentioned a method to calculate the integral called the Gaussian quadrature. So how do they do that? They just pretend the the differentiations of the du as the wx, and do the shift from denominator, and we can transform the integral form from this one to this one, and use the Gaussian quadrature to calculate by the discrete way, by summing up.
Yeah, so you
back
should,
to the
yeah,
question that
you should investigate what's the detail about Waverly transform. Yeah, because you didn't understand at all. Right? The whole principle, what kind of Waverly transform representation of the original signal? What's the idea of each step, right? So just list a bunch of computational steps. We do not necessarily memorize or understand those steps, but we do need to know its logic, right? Yeah, let's move to the next slide. It's the minutes to discuss this.
Okay. So in this part, I just want to present in a graph way. So pretend here is the original subspace after we transformed our data in, and we will need to do two things. The first one is to transfer our data, filter our data to a smaller subspace, which means we filter the signal by the filter to a smaller data, and we will use the Gray-Schmidt method to calculate the wavelet here, and we will do the same thing in the V in the subspace of there, and do it again until we run out of the data. So by this way, we can get the frequency information, static information from the data. So here is the graph perspective.
So I mean, every time, every iteration, you're gonna use the basis in V1K and W1K to do some filtering and get the information, then pass to onto next step. You got V2K and W2K until you got VNK and WNK. Is that the general procedure?
Yes.
Okay.
Yeah, and after they run off the data, they will need to construct it by the same versus inverse way. They have to sum them up to get the original data, and sum them up to get the original data, and do the again to restore the data back. And in the end, they can get the U we want to get here. So
Where do they embed kernel K?
embed kernel K where?
I mean, in this whole procedure, how is the information of K is integrated into the computation?
The K, you mean the K over here?
No. In the previous slide. Yeah. So
Is
here,
what?
our goal is to use Waverly transform to compute this convolution, right? So you need to use A, you need to use the kernel K, right? And how does this whole computation?
No, we don't. We use T. We transform the A to the wavelet space, and we we assume the T already we use the T when it is in the wavelet space. Tn over there, they use NN they use neural network to present it.
Okay. I got a general idea. So actually your discretization of the T has included information of K. That's why they use neural network.
Yes.
The implicit
exactly. The same as the one in the Fourier transform. They do the same thing. They don't need to calculate the kernel matrix. They use the neural network. They just use weight in a Fourier space.
So the Tn here, I mean, traditionally, if you know the form of K, you should have some discretized method to compute Tn, right? But now because you don't know K, you want to represent them with some flexible model. That's why you model AI, BI, CN, and the T hat by neural network.
Yes.
Okay. Yeah, that's a big picture, Sui. If you cannot get to the details of a computation, at least you should tell us the big picture.
Okay.
Yeah. Go on. Yeah.
So next I'm going to talk about the architecture from a code perspective and compare with the AlphaGo. So basically they are the same, I think. But the black box over here are different. The rest of parts are the same. So in every black box, multi-wavelet transform today consists of couple items: the decomposed, linear part, and reconstruct part. This part, the decomposed part and the reconstruct part, is similar to the equation over there. So we will do the decomposed again and again with the operator. And in this part, we only do one, the linear part.
So each decomposed block corresponds to one step n. Is that right?
Yes. Yeah, exactly.
Okay. So when you proceed to the next decomposed block, you're proceed to the next V1, V, NK, and WNK, something like that.
Yes.
Okay.
Yes, they will just do again and again until they run out of the data. So after they filter the data once, they will use the output over here into the next decomposed and just keep filter the data.
That will correspond to another polynomials, right? And they're orthogonal polynomials.
Yes, different polynomial orthogonal. Yes.
Okay.
So here's much more detail about the black box from decompose and reconstruct. I think we can skip this part. Yeah. So we can just tell the result. From the result, the wavelet transformed is better than the FNO, the green dye over there. However, we can tell not every polynomial set can meet sorry, can meet the same effect, like they use another polynomial set. They meet
Lag means Legendre, right?
the gender, yes.
Stage
And
B
the
is Chebyshev.
Oh, okay. I don't memorize the name actually. So I want to mention not all the polynomial sets can meet the same performance. And
Okay.
in high dimension data, we can tell the same things. So especially we can see the RNG of there, another polynomial set, the performance is way worse than the FNO.
What does it mean for random? Oh, random
Another
the random entries of future matrices. Oh, this is basically a very bad thing, right? Because the future matrices are not computed by some smart procedure. It's just fill the entries by random numbers. If you can look at the caption here, MWT R&D instantiate random entries of the future matrices.
Oh. Okay, anyway, this way sucks. So let's move on to the high dimension part. Yeah, and we can tell the Legendre can still keep the better way than Fourier even in 3D part. That's it, and they can still they have the same feature as the FNO. They can keep the invariant feature, which means in this part, which means when we change the resolution, we can just always keep the arrow not be divergence. That's it. So let's do the little conclusions. In this paper, they present another method to approximate the kernel integral, and they can meet the better performance. However, they didn't mention how much time they take, because from architecture, the neural network there, they have to build for neural network in in every loop. I mean, they have to calculate each every loop. That will be a time-consuming behavior. And
so AI, BI, CI, and this T hat are modeled by different nets. If you vary I, like I from 1 to 4, in this architecture, you're gonna have 4 different neural nets for AI. Also for BI and for CI, and also for T hat.
I think so.
Okay. But its performance is much better, right? If you take a look at the table.
Yeah, they can meet lower they can meet the lower error, but they can meet the lower error, but I think the speed will be way slower than FNO.
Okay.
Yeah.
So they only test on the Navier-Stokes and Darcy flow.
No, they test on more experience, but I only present 3 from the paper.
Okay, their performance on Darcy flow is impressive, right? It's 1 order of magnitude smaller than FNO.
But it depends on the polynomial set. It's hard to set on other PDE, the
Oh,
Legendre
okay. If you use
bit.
Chef, it's actually similar. If you use Chef, yeah, it's kind of similar. It's just slightly better than FNO.
Yeah.
Okay.
Is this wavelet operator resolution free? They show the results of super resolution.
So
Because,
what do you mean?
So in the FNO, they can do super resolution. That means their method is independent from the input's resolution. So you can give their training data as for dusty flow, for example, you can give the input data as s equal to 33, but you can also output the resolution of 512.
Oh, you mean training by 32 and apply it on 512?
Yeah, it won't work very good, but FNO can do this. So does the wavelet the wavelet operator can do this?
We need to answer the question. We need to understand what's the details about wavelet transform. Right.
Okay.
Yeah, I have to check the paper again. Yeah.
Okay.
Sorry. Oh, sorry. One question. What's the T in the last figures? At the top of the neural the networks. What's the T means?
Where's the T?
The last figure.
Table 3.
Table 3. Yeah. What at the top?
Here means so the test setting is like this. So I'm gonna use the solution at 1 time step and then predict the solution at big T.
Oh, gotcha.
Yeah.
Okay. Thank you.
Okay, so this is the presentation today.
Okay. Yeah. Thanks, Sui. But I think after that you should take a close look about the
measurement. Yeah.
Okay. Yeah, the whole wavelet formulation and computational procedure. Otherwise, we're gonna still. But we know the general picture now.
Okay.
Okay.
Thank you, guys.
Okay.
Yeah. Next, I think we have Tushar.
Yeah. Hi.
Yeah, Tushar, you can share your slides or notes and start.
Yeah, because I'll present from the notes only because the paper was a bit all over the place, so I had to write everything like in simply that I could understand.
Yeah, sure.
See if I can share from my iPad. Yeah, it's visible now, I think. Yep, so it's visible all right, like you can see full screen and everything.
Yeah.
Okay, yeah. So what I'll be discussing today is the general neural operator transformer for operator learning. So it's like short form is called G0, this thing. So, but first what I'll do is I'll start with self-attention because this forms the basis of everything in the transformer in this. So what basically is like a self-attention? In a simple terms, it's just a sequence to sequence operation. So if you think about it, you have some sequences, call it x1 vector, x2 vector, different amount of different vectors. You pass it through something, just call it something, and you get another set of vectors in this. So I'm assuming you have t set of vectors. Each vector of dimension is k, right? So this is what just a self-attention is. It takes in a sequence, outputs a sequence. now the little bit more details as to how it does that. So first it does is it takes average of each of these vectors. So to compute y1, it will take some average of x1, x2, x3 of all those x vectors in this. So for just a moment, when understanding self-attention, forget about neural networks. So just for a moment, so these weights, these W's that I'm saying, it's not learnable. So this is what the self-attention idea has been very, very like, it's a very old idea. It's not a new idea. So how you can get these W's, a very simple idea to do is just take a dot product of two vectors and get some weights. So, but the thing with this is this dot product can range from -infinity to infinity. So to squish it down to something that is between range 0 to 1, just pass it through a softmax in this. So this is just what like a self-attention is. Like this is the self-attention. So now how the neural nets come in here is that if you look at this, there are three things that are happening in this. The first one is each xi is compared to other vectors, that is other x values, to establish weights for its own output yi. So like to get y1, x1 is used alongside other vectors to get some weight in it for this. Another thing where x1 is used, it is to compare with all other x's to get some other y. So this is the second thing that it is doing in this. And the third thing is that the final that we do is it is used as a sum of a weighted sum to get the output vector, this thing. Each x is used, the weights that we had to get y in this. So the idea with this was that how can we smartly do these three things? This is where neural nets come in. So what they do is they take some xi, let's pass it to a neural network with some learnable parameters and get something called Q. That's a query. That's what they call a query in this. Take the same xi, pass it through another neural network and call it a key. You get another value k. And another, pass through a different neural network, get a v, this what they call it as a value in this. So now essentially earlier where you were using x to get these things, now we can replace this with a query and a key, where instead of this being fixed, now it's a learnable thing. So it can learn from data itself. So you don't have to manually figure out what the query or the key or these vectors, x vectors should be. You can give, and you have an input, you have labels to that, and you simply learn these query keys and values from that in this. So these operations are same. W is very similar to, it's very similar to this. So if you see this only thing changes is x changes to q and k, because we want to learn these things, what these things are. And this is just for stability. They just divided by the length of the vector k, just for stability. This is just scaling the dot product, nothing much in this. And then they do the same thing, softmax of the weights, and then multiply those weights by, multiply those weights by x to get the y in this.
I think the xj should be replaced by vg, right?
Where?
I mean, the last line.
This one?
Yeah, I think once you get this w, compute the dot product between the query and the key vectors, you're gonna multiply with vg, the value vector, right?
Oh, yeah. Yes.
Standard,
yes.
Standard attention.
Yeah. Sorry about this. This is v. Yes, this is v. So multiply by value. Yes, yeah, in this. So this is what like the self-attention is. This is the what we call it as self-attention block in a neural network, like in a transformer neural network in this. Now from this, the extension to this is called what we call as a multi-head attention. So self-attention, if you look at it, is take some x with t different sequences, each of length k, pass it through a self-attention, and you get some other sequence, t sequences of length k. So what multi-head attention is, run multiple self-attentions in parallel with independent neural networks. And afterwards, what you get is you get 3 sequence outputs, concatenate them together, like vertically, run it through a neural network just to compress the dimensions back to k. And this is multi-head attention unit what they call in this here. Now the G0, what they are doing in this paper here. So this is just an overview, a big picture of what they're doing. I'll then discuss each of these parts in detail one by one. So first is just the terminology. They have something called, they call it encoders. These are the input encoders. And then they have a heterogeneous normalized cross attention, which is very similar to a self attention, just a very small change in this. And then bunch of neural nets. And then this is the normalized self attention. That's a normal model. And all these details, skip connection, that's just an architectural details. So in this, like in this presentation, what I'll discuss is encoders, what the encoders are. And first of all, I'll also discuss these things, like what do they mean by the vectors, shapes, functions, and how they're using query points and all these things. Then also an encoder, what's the point of an encoder? Heterogeneous normalized cross attention block, and the gating, what these things are. So this is what I'll discuss in this. And then the G0 is just about attaching all these parts together to understand, just getting the results from this. Yeah, so first the problem formulation. So G0, the first thing is the query points. So these are those points here you mentioned in this. These are the query points in this. Some query points, I think they haven't mentioned this in detail, but I think in DeepONet, something that we pass through, I think it's called the trunk or branch or whatever, those X points where we want to evaluate the Y function. I think these are those query points here, but they haven't mentioned any details. Like the paper, it lacks a lot of details. They don't mention a lot. They just assume that people should know all these things. So I might be wrong, but I think this is what the query points are, those X values. And then because
is the query points have to be evenly distributed?
No.
No, it's just a bunch of points. You can choose it. Okay.
Just as DeepONets. It's just a deep, like whatever you see in DeepONets, because it's a regression problem. There is no Fourier. You're not moving into a Fourier domain so that you need equi-space point. Nothing like that. It's just a DeepONet. Whatever you can do in DeepONet, you can do here also.
It doesn't have to be a mesh. Okay. Yeah.
So the only thing, the different that they're saying from DeepONet is that first thing that's that they're using transformers, which they say is more expressive than a simple neural network that DeepONet uses. And another thing that they are saying is we can incorporate multiple informations. DeepONet can also do that with an extension. I can't remember the exact name, where they have multiple branches and multiple trunks, things like that here. But what they are saying is, yeah, the transformers can do that better as well in this. Right. So like these are the query points. Now the functions that you have, something that you can have is an input function, where maybe you want to map from, say, U0 to U. U0 can be anything from one function to another, and additional information. So this is where they say that it's a little bit different. You can also use some kind of additional information. As an example, I'm going to take a boundary shape. So in some problem, maybe the shape of a boundary is very important to the solution in that. So you can have a boundary shape, let's call that xi dash with different points, means each point what the boundary shape is. And then you have a final solution that you want to learn it to in this. So the task.
What's the assumption about their data? So they're assuming that, okay, you got this input function, but in practice, you're going to still sample the input function, right?
Yes.
It's not necessarily, the sample location is not necessary to be the same as xi.
Yes, no.
And in whatever way you sample the
just like DeepONet, you have to just, this is a discrete function. Like you take some points. It can be anything. It doesn't have to be. I think what xi relates to is maybe, I think it relates to U, where these U solutions are.
Okay, so you can training output is just a set of U samples at the query points.
Yes, I because they haven't mentioned any details in this, and I have to look into the code to understand how the implementation work, which I haven't done at this point. But this is what I think it is, just like getting the understanding from a DeepONet. Because in DeepONet, if you remember, we have some points goes through a trunk, and then we have a function here that goes through a branch. Then we multiply them together.
Yes.
Gets U. So these U and these points are related in this, because these U is the evaluation at these points.
Okay.
right? So this is what I'm thinking. Maybe these query points are these, and then U is this. I think this is what I think maybe it is. I have to look into the details to be sure, but it looks like that this is the thing in this.
Oh, so their whole input will be the concatenation of the U circle samples and the boundary shapes.
No, they're
No?
using different. It's not a concatenation. So that's what they're saying. You don't have to concatenate in like a transformer. In transformer, you can provide these information separately.
Okay.
Yeah, so that's what I'll discuss later, like how they're incorporating these things. It can have multiple. That's what they're saying. It's not necessary that you only have to have two things. You can have after this maybe some other parameter of the model that you already know. You can all
Okay. So the boundary shape, my understand that okay, you're gonna just sample the boundary points.
yes,
Provide at least the boundary points which reflect boundary shape, right?
yes, yeah.
Okay.
If you think that this boundary shape is necessary for the solution.
Okay.
So like, and you can have other things also in this, like anything that you think is helpful for the solution.
Okay.
But for this example, just to understand, I'm just taking these two examples, input function and some boundary shape. But remember, like we are not mapping from boundary shape to solution. We are mapping from U0 to U, but we want to use these domain knowledge that we already know that the boundary shape should be like this.
Okay.
Right. And then it's a simple mean squared error. G is what they call it, the G0 operator learner, whatever. So A would be U0, Xi, all these values there. In somehow we're going to use all these values and then get a final solution to this. In this.
Okay.
So, and yeah, so now the first thing is input encode, this thing, encoders, like what these encoders are. So like, for example, this is the thing they're saying. You can use a shape, you can use some other function, whatever you want. You can use the edges, like you can use anything in this, but the mapping is only from some U to U0, some U0 to U here.
What do you mean by some U0 to U?
Means some input function to some.
Oh, okay.
Some whatever, like.
So,
but
so edges and those so-called edges, the boundaries are just auxiliary information.
Yes, yeah. Yes. So these things are all like some auxiliary something.
Okay.
So now, but the thing is that now the encoders, like what these encoders are. So the problem here is that the query points, you can have query points, say from so you can have query points from 1 to NQ. Some NQ is some number, some query points here. The input function, say like it's the Xi and the evaluations at that point. So X, those values and evaluations at that point. This can be something else, Ni, some number, a different number here. Boundary shapes, they can also be different points, NB here. So the problem that they said is that these are all different dimensions. So if you concatenate them like this, and in your solution, you have now, if you want to train it on some set of values, you cannot, if then when you are testing it after training, you are restricted to the same number that it was trained on. You don't want to do that. You want to use different numbers in this here, right? So you want to use different numbers, or like what you want to do is like here in this, what they do is that just to make sure that these values, like these different values, if you concatenate them, it will create a problem in this. So to resolve that issue, what they're doing is they're using some input encoding to resolve this issue. So first they do is they push these queries through a neural network to get Q. This is where the Q and all those things come in, Q and Xi and Ui. So this will basically be like a matrix where this is Xi and here it will be Ui dot. So just a matrix, those two, and output you get is run through two neural networks to get keys and values. This is just the nomenclature. They're just using these numbers here in this. And also like the other boundary shapes and whatever you want to use, run it through a network, get keys and values.
So N here is does it contain nonlinear activation or just some feed-forward network?
They have written it as a FCN, fully connected network. That's it. They have not mentioned any details, like what it means.
So they're gonna treat the output. So through, for example, through here. So here they will, this is a Q matrix. I mean, the output as Q matrix,
Yep.
and through this and this, they will the output as K matrix and V matrix.
Yes, yes.
So they want to do some heterogeneous cross attention.
Yes. Yeah, exactly. So now they have Q, K, V. So next is now these neural networks, that's what they're calling encoders. Like this is what they call encoders. And the only thing that they've mentioned is that the purpose of encoders is to bring the dimensionality down to so that all those key values and queries have same dimensions.
So XI is the query points. That is the training output
Yes. Yeah.
locations, and this guy are the input
Inputs. Yes.
Okay.
And you can have auxiliary inputs as boundaries and nodes or whatever here.
Okay.
And now the main part, this is the heterogeneous normalized attention. So the only difference between, so like from encoders, now we know that we have queries, we have some keys, and we have some values in this. So now in a traditional way, the cross attention, that would be called it like the self attention was where the difference between self attention and cross attention. In self attention, queries, keys, and values, they all come from same X here. In cross attention, you get Q from different input, different sequence than keys and values. That's it. That's the only difference between a cross attention and a self attention in this. So now if you run, like just for sake, like we are running a simple cross attention where you get Q, you get some key multiplied by key. This tau is just like a normalization. So this is nothing. So this is the same thing you're doing dot product. Then you're taking a softmax. Then you're multiplying it with values V. So this essentially is that a self-attention or cross-attention operation in this here. So this now what they said is that the order to compute this thing is N, M, NE. So what is NE? NE is the output from these dimensions. So the Q could be, say the values like it's NQ. So there's some NQ dimensions, right? So the output would be NE. So number of points times NE. This one. So the output of
Tushar. So I mean, like for every xi, you got a Q vector, right? For each xi, you got a Q vector. Now you are gonna compute the dot product between the Q vector with every K vector here.
Yes. Yep.
And you're gonna enumerate all Qs to calculate their similarity.
Yeah. So like Q and K. This will be
But how do you like do the weighted average according to V? Because your one Q, say suppose this one is a Ni, right? One Q will get Ni such similarity, right? You got Ni V's, but if you have multiple Qs, you got like NQ times Ni similarities, right? But you still only have Ni V's, right? How do you finish the attention, like weighted average?
I think the weighted averages across each row. So if you look at like the attention that they compute here is that this thing, it's for each row. Like for example, this is like, just look at the transpose of this. So this is for each row. So if you look at this here is in this thing, let me write it. So Q.
Oh, okay. So you want, okay.
Right. So we are taking only one. So it always be 1 cross NE, because we are ensuring we're running through a neural network. So all these things would also be 1 cross NE. So like each row we are computing.
Yeah, I want to have a comment here. So for KQV, for all the features, the embeddings, they have the same dimension across the whole transformer.
Yeah.
Yeah, so that's why they can do the dot product for each feature. But the number of the query value and and the K can be different. But for the self-attention, the number are the same.
Yeah, but my question is that, okay, for one particular Q, right? For one Q, we can calculate the similarity with each pair here, right?
Yeah.
Now you do a weighted average. That's for whom, right? If you calculate similarity and then you do the weighted average according to V, you just got one vector, right? And this vector represents what? Represents something corresponding to the xi. So suppose you got you have like nq query vectors, and after doing this cross attention, you got nq vectors. Yep. Am I right?
After doing what you say, after running it through like a neural net?
After running through the cross attention, because each Q, for each Q, you're gonna do the similarity, calculate similarity with all, say, n L vectors here, right? Now you do a weighted average with the corresponding V vectors. You got one vector. That's one vector just corresponds to this particular Q. Right.
Yep.
So if I got NQ query vectors, it will end up with NQ weighted average, right?
Yeah, this part is goodbye.
Yeah, I'm just curious to know like how what's the result of your cross attention.
Yeah,
So
because
the resulting vectors, the number of resulting vectors will be the same as number of queries here, right?
Yes.
Is it correct, Xin?
Yes. Yeah. So okay.
Then that makes sense because you are actually literally have like NQ observations, right? For this particular example, training example. So for example, for a particular query point xi, you have a qi, right? So you're gonna calculate each qi with some key vector, say kj, right? You normalize it and you get some weights, right?
Yeah.
And then you multiply with the corresponding vj, and then you do the weighted summation over all the vectors, value vectors here. You end up with one vector. If we denote it by ui, it will just correspond one ui, right? So
yeah.
suppose you got 10 QIs, you got 10 UIs.
Yep. Yep.
Okay, similarly, for the shape points, you got another 10 UIs.
Yes. Yeah. Yeah.
Okay.
Yep. Yeah. Yeah. So like in this thing right now, like what I'm discussing in this part is just look at a pair of them. So for now, just look at this pair, or you can also look at like this pair. Sorry, these two. So like these two separately, you don't compute all three together. So one pair will do this, another pair will do this, and then we combine that using what is written here as gating. So that I'll discuss later, like how they are doing this. Like there's so many details in this that's why I had to write my own notes just to simplify what is working. And even now I have to look into the code to understand how they've implemented all these things in this.
Okay.
And they've not mentioned in great detail how all this works and what, like, for example, this is the part now after this, what I'll discuss now, these parts, this is where I was a lot confused here because they just give results and they never mention how they got this thing. So like, for example, like in this, if like, is this point clear? Like, or do you still have confusion in this, in the standard, if you do standard self-attention operation or cross-attention operation here. So like in this, you get this. So they say that to do this operation, the order to the cost is, the order is N, M, and NE. So NE is the dimensions of embeddings. So Q would be N cross NE. K and V could be some other M cross NE. So the output is NE. always in this. So the problem is they say that as a PDE problems, in the PDE problems, we can have N and M. This is the points that we have. This point on the boundaries or number of query points. This could be millions or billions, like it could be a really large number. So if you look at this scaling is actually order of N square. It's a quadratic scaling. So this is really bad. You can't have a quadratic scaling. So for this, they have proposed a modification here in this. And in the paper, they just mention these modifications with no explanation as to how they come up with this thing. And even like if this thing is even right. And I tried to find the way. So like, let me just explain what they did. So what they do is instead of first computing the dot product and then the softmax, what they're doing is they're computing softmax first of queries and keys, only queries and keys, because softmax is a simple operation and because you're just doing it row wise on this. So they don't take into account of any order of whatever cost is to do this, because they haven't discussed cost of this, what cost should be of this part. So I'm just assuming that because it's like on each row, you can do it independently. So maybe they are just saying that it's an embarrassingly parallel thing. So let's not talk about the cost of this part here. And then what they do is like they say compute the attention without softmax. This thing is just normalization. Whatever is at the top, just normalize it. So they say that take a dot product, another dot product with VI in this here. So this, and they say that this thing can be written as, so this XT is just a normalization. Alpha T, sorry. Alpha T is just a normalization. Take it out because it's independent of I. It doesn't depend on I here in this. So sorry, it doesn't depend on T, what it should be. So like for each T, they say like it's fixed in this. Take it out. We are left with this. And then they straight away jump to this. This, I could not understand how they came up with this part in this.
One thing, Tushar. So QI is the query vector for query point I, right?
Yes. Yeah.
So they just do softmax over this query vector.
Query vector, yes.
So if your Q matrix is like N by NE,
yes,
you just do it row wisely.
Yes, row wise softmax, yes.
And the similar things happen to the K matrix.
Yes.
And then, but after that, they still do this dot product, right? If you want to compute the attention score, right?
Yep.
You can still multiply with this, and then they do the normalization. What's the difference? The only difference is that you don't take exponential on that, right?
Yeah. Yeah, that's the only that, because how they justify the performance is they straight away jump from this to this. And then looking at this, I can understand, okay, if this condition is true, then yeah, this works. But I couldn't figure out how they converted these two things. And they have not mentioned anything how they did this in this. This is where I was really confused. And I tried looking up if there is some kind of inequality that connects dot products to Hadamard product or something like that, but I couldn't find anything. Is this some kind of linear algebra inequality that I don't know about?
What's this? This is a Hadamard product.
I think it's that element wise, whatever they call.
Sorry, one question.
Yeah.
So how do they do the normalization from this to this?
This is just the term, like, so this, they just call this term alpha T. I mean,
so yeah, I mean, how do they how do they transfer from this term to this term by the normalization?
Yeah, okay. So this term, right? So this term here. So what they do is they call 1 upon whatever the sum is, Ki, whatever, is equal to alpha T. Because you see, you're summing in J, you're not summing in T. So this is constant. So they just call this alpha T, whatever this 1 upon the term, whatever the term is. And
do they sample from distribution or?
They haven't mentioned anything. They just said that let's call this inverse of normalization as alpha t, bring it
Yeah,
out.
because for my understanding, like normalization is always is sample like a normal distribution or random distribution or even distributions. So
You won't need that, because if you know these q and k vectors, you can just compute you can just dot product and sum them,
oh, okay.
because you know these queries and key values. This is where this is what these things are in this.
Okay, this is dot product, right?
Yes.
So this one is QT. Yeah, go ahead.
I think that's the Kronecker product with
Uh-huh.
the circle and the X cross, and that's just showing that you can rewrite this as a matrix and then sum over that matrix and it will come out to be the same thing.
Yeah. So but I don't know how they come up with this. Is there some inequality that I like?
I think this is a property that you can actually use based on the multiplication of dot products and these indices.
Okay, because I couldn't find it. I tried to look and this is Kronecker product. Okay, this is another thing that they have not mentioned any of this, because in computer science, sometimes they use these cross with X as an element-wise product as well, Hadamard product.
Okay.
In a lot of the literatures, it's element-wise also.
Do they explain what does this operator mean? Is a Kronecker or dot product advice?
Nothing. No, this all this section is hardly 5-6 lines. They have just mentioned lines after lines that this is the compute softmax without compute first softmax, then dot product this, then this, then this. Now if you look at this, the order is this, that's it. They have not mentioned anything how they come up with this, if this is an inequality, what this means. They've not mentioned.
I can make some comments here. This trick is called the linearized attention, and actually what they're doing is when you compute the Q2 and multiply the KI, it's actually doing the computing the similarity between the query and the key. Actually, it can transfer to some kernel computation, and if you can define the kernel, with some something like the random from your feature or something, and you can do these things. Actually, I think I gave a talk also in this seminar, I think 1 year ago. If you are very interested to detail about this, you can check my slides at that time, and also in the GitHub of the seminar. And I think at one slide, I gave a very detailed introduction about this linearized attention trick.
But what's that? It's a Kronecker product. It's a dot product.
It's a Kronecker product.
Yes, still for my understanding here, so the new ZT is exactly the same as the previous one, but it just provide some more efficient computation.
Give some minutes. I can open the page and I can share the screen with you to give this.
Yeah.
But maybe Julia, you can go ahead first, and I can just send that slides to all of you by the email, and if you're interested, you can check the detail.
Okay.
If I can find it right now.
Yeah, no problem. Yeah. So let's just assume that you can. This is a equality that we know. You can convert 3 dot products into a Kronecker product of sum of Kronecker product and then a dot product outside. So then they say that this Kronecker product, it takes order of m n e square. So the difference is that now in square of n, n squared n e, they have changed that to some n e squared, because we can control the dimensions of embeddings. It's a neural network. We can control, we can make it small. So they are shifting the order of like cost computation from n to ne. So now they say that it's now linear in m and n. So you can have larger sequences of millions in this. And
this one is I mean, so is this this is a dot product or
dot product?
But this one is matrix, right?
Yes.
And this one is a vector. How do you do dot product? This should be matrix vector product, right?
Yeah.
This is 1 by n.
No, it's not. It's not. It's this. This is not a matrix on the right side. Like this thing is vector, I think, because they are summing i's.
Yeah. The question is, if this analyzed product, this is a vector, right?
Yes.
And if it is a Kronecker product, this is a matrix.
Yeah. Yeah.
So what does it mean? Right? Is this analyzed product or?
So like I think if you assume that this is a Kronecker product and this thing is a matrix.
Yeah, I feel this should be analyzed product, because if you write it down, it should be something like that, right? It's some constant.
Yeah. Yes.
Is EI, and then you times CI, right?
Yes.
And intuitively, it is equivalent to you first do the analyzed product with BI and CI, and then multiply with A. It should be like that. Yeah.
Yeah, because in a lot of the CS literature, this cross is element-wise product. So, but they haven't mentioned. Maybe they assume that we know that it's element, but they should know that this is also the Kronecker product is also the same symbol.
So this is usually referred to as a Kronecker product.
Yeah.
Actually, this is pretty easy to show. Right? It's pretty easy to show. Like, if you can write it down, it's AI times BIJ, and then times CIJ, right? If you just do some J, right? If you move it in, yeah, it should be pretty easy to show that.
Okay. Yeah. Okay. Yeah. So then this should show that the order to do this is m and e squared, and then the dot product, it's simple n and e squared in this. So now the order comes out to be m plus n. So now this thing is linear in m and n.
But if this is an analyzed product, how is the complexity is NE squared? The analyzed product just give you
Yep, it should be.
right?
Yep.
They will have m vectors as them together should be m and e.
Yeah, I can have a comment here. So for the Ki and the Vi, actually both of them are the vector. So they do the connector product and get a matrix. So assume for that, because the dimension for Ki and Vi are both Ne. So the dimension for the matrix is Ne by Ne. And actually for the I is that there are the number of the Ki and Vi are M. So that's the M multiply Ne square. Yeah.
Yes.
So this is still the Kronecker product.
Yes.
Yeah. So like
because this one is not dot product. It has to be matrix vector product.
Yes.
Then it has to be matrix vector. Yeah. I mean, maybe they have to push it like matrix, and then because you can't pre-multiply, and you can't pre-multiply.
Yeah.
In this.
Yeah.
So the A would be like, as you mentioned, is NE. And if you look at V matrix, so this is also times NE. And you're saying that the Kronecker product should result in NE cross NE. Right. So like this Kronecker product, if I went through a Kronecker product, it should be NE cross NE. And then if I take sum, does that convert to a vector then? If I'm summing it along in one dimension. No.
So you're doing the Kronecker product of a 1 by NE, Kronecker 1 by NE, or to generate that n by NE, and then you're summing over each row for K and V.
Yes. So we can think regard this as we do the connect product in the dimension 1.
So
and then do the summation in the dimension dimension 0. Yeah.
Yeah, so it's like
This is the Ki and the V and the Vi. Yes.
yeah.
So the benefit of wiping off exponential is that you can apply this trick.
Yes. So this trick
Okay.
and that reduces the complexity in n square to n, but it shifts the number of embeddings.
Yeah, I still want to have another comment here. So I think whether this can be more efficient depending on the NE and the number of NE and NE and the M and N. So for example, if the transformer has a very, very large dimension, so for example, for the NE, that can be somehow like the 4,000, and then this may be more. The computation would be more expensive. But I think for this transformer, for the G node, actually the M and N can be large, but the dimension of the hidden space, the hidden state can be small. So for example, the NE can be just 64. Then it will reduce the computation a lot.
Yes, yeah, and I think because what they're thinking is that they can keep the dimension of embeddings small because our inputs they are like low dimensions. So like X could be 3-dimension in for a physical problem there. So you don't need very large embeddings, unlike if you're mapping it from like some words, some dictionary of words that you're trying to learn in that. Then maybe that's their thinking in this.
I think she can share his slide, and his slides are very clear.
Okay. Yeah.
Shikai, you're muted.
Can you hear me right now?
Yeah.
Yes. Yeah. So this drawing is about the transitional attention. So you have to do the computer matrix multiplication or of the computer similarity about Q and K. So right here you have to do the matrix multiply a matrix. So time square so is OT square. So T is the number of your the sample or token or something, and then do a softmax and then compute the similarity or your attention weighted by multiply the value. And however, the linear attention sounds like, because when you check the formula about the original attention, actually we are doing here, do the multiplication about Q and K. So in a general force thing, we are computing the similarity about the Q and K. And actually, it's something like the EXP, QK, GA, something like this one. And EXP this way is something can be regarded like the kernel computation about the Q and K, because for some kernel like the Gaussian kernel, RBF kernel, we are doing something this way. So how about and the linear score something like that? How about we just do the something like this called the kernel, something like the kernel trick. We do the kernel smoother on the Q and K. Don't do compute similarity, but first do something like the kernel smoother. Use some Gaussian, use some other things. They use this function to smooth the Q and K together, and to mapping them to some they call the what's this thing? The infinite dimension or something. It's called the kernel trick, and then they compute the K and V together. And because V is something like I think it's a vector. So right here is not a matrix to multiply matrix, but matrix multiply a vector. And here it becomes from the square to the linear complexity. And then you combine with the query together. And then you blend the OT square to the 2OT. So from the square to the linear.
And to the following question, whether this thing is Kronecker or like element-wise product or Panama, you can check the initial paper here to give the formula. Here is the general, okay. The formula 4, you can see here is the original the attention equation, and it can be generalized to a kernel computation or similarity computation to the equation 5, and it still multiply Vj here. And what they're doing, the similarity computation about the query and the key can be multiplied to can be transferred to some like the smoother over the Q and smoother over the K, and then multiply the Vj, and you put the Vk Qi in the format, and here is it. So you can see right here is the multiply the over n, the smooth over the key and the query. So here is something like the Kronecker about between the K and the Vj. How to say that? So I think that this thing is something like the Kronecker product, because you want to over go through all the n right here. Sorry, it's a little bit confused because I didn't remember much detail, but you can check by yourself. Yeah.
Yeah, I think the K is in the equation 7, right? But the problem at the first side is how do they put Vj to be Vg transpose?
Yes.
But I think it's a pretty straightforward linear algebra issue. It's not a big deal. But this was proposed by other people, right? They just apply this trick.
Yeah, it's a very classical trick in their attention series work.
Okay.
Yeah.
Okay. Thanks. Sure. Why not you just go on?
So after this, once we have this modification, which basically the idea was to turn the quadratic complexity from n to ne and make it linear in the number of points in this. So this was the main purpose of this modification. That's the main purpose of this. So now if you remember, this is for a pair. So if you look at this, so what I'm doing here is that this is for one, have multiple keys and values. Queries is same, it's always one because we have one set of query points. Keys and values, we can get these from different things. We can get it from your U, we can get it from a boundary function, we can get it from different things. So how do they combine that is like, because we can have it from different embeddings that they just take, is like they just show that this can be incorporated in there. Basically, they're just summing it all over and then just averaging it.
Oh, it just adds up.
And in this, they're saying that the complexity remains linear in number of embeddings as well in this.
So are they assuming they're assuming their key value, the Q and the K and the V vectors are all of the same dimension, which is NE.
Yes.
But why they add up their query and vector and value vectors?
Yeah, because they say that they have multiple keys and values. So like multiple.
I understand that this one are just the tension result, right? You do the weighted average.
Yeah, it just average. Yes.
Each pair of inputs. And then this one is you can view it as the input, the query locations, the representation of query locations, and they add them together.
Yeah. They haven't mentioned why they added in this.
Yeah. Okay.
There are no details. Like they do a very similar thing in gating as well. So now this, as I mentioned, like this is how they combine those different things. Now the geometric gating, they say that this idea is inspired from domain decomposition techniques, where this is also, I think, similar in X-pins, where they have multiple pins focusing on subregions and things like that there. Yeah. So they're trying to somehow use this technique in here as well. So what they say that for this is that, so get a query coordinates. So this would be like different neural networks, K different neural network. This would be K is the number of domains or however special networks you want in this K, and run it through the query points to get some G values, which they call like coefficients in this. And then after each output, you get some Z in this after each attention. So what they say that, okay, instead of using this Z as it is, why not pass that Z through these special networks so that these special networks are learning different things. Take the average of those. So how this is computed is using this coefficients. This, I think, is again a softmax of whatever coefficients they have set that, like, this is just the weightage of each network. So if this is the input, this network, special network will have this much weightage, this special network will have that much weightage, like different weightages to different networks. Here also they add ZT at the front.
That's the residue. So XT is the query point, right?
Yes.
So your so assume your output dimension of your gate is K. So you give this GI, why this GI? So for each gate you got a one-dimensional output, right? Then you do the normalization.
Yes.
And EI is okay. So it's like a mixture of expert, right?
Yes, mixture of experts. Yes, exactly. Yes, yeah. Mixture of yes. In this. And so they just say that this is like learning, like, so another thing they mentioned that is that these does not have to be from networks. You can have some prior knowledge to fix these values. If you have some prior domain knowledge that you can use that. And they said this is also something similar is used in XPins, this thing. Yeah.
But this is how do they like associate this idea with domain decomposition? They don't have any domains, right? XPin.
Yeah.
You need to specify where the subdomains are, right? They don't just assume virtually I might got like some K subdomains.
Yeah. They're just saying that they're hoping that those networks are like that. The first term they say that is the mixture of experts. That's the technique and then they mention it is also very similar to domain decomposition techniques. And then they refer George Kanedakis' few papers of soft decomposition, domain decomposition, something like that. In this
doesn't make sense.
Yeah, it doesn't. I couldn't understand because this is nothing different. They're just mentioning this in this also.
Okay.
Yeah. And then like finally the results, what the difference in the results is. So like, yeah, so MIONet, this is like a version of DeepONet with different number of different.
One another thing, Tusha. Can you go back? So once you got this ZT, ZT is your prediction eventually, or you use some FNN, like feed-forward network, to give the final prediction of the target function value at query point.
So like you can see in the architecture here. So like after this, they get ZT and then they again pass through. I think this is where those different these are those FNs where the gating is applied, and then
they add them together.
Yeah.
And then they do they're gonna do a additional layer of the attention again.
This is the self-attention, because now here the thing is that now you get Q, K, and values from different inputs. In this case, it comes from the same input. So they say that this is now self-attention.
Oh, okay. So they actually got to the ZT for all the query points.
Yes.
Then they do one layer self-attention.
Yeah, because they
put it in FFN. I guess that will be a channelized FFN, and then to give the final outputs.
Yeah.
This is also a residue block.
Yeah. Yes. Yeah. They say that we also have residual blocks so that the gradients don't vanish and things like that in this.
Okay.
So now this the results. So MIONet is some kind of special DeepONet with multiple branches.
Hey, what's your question?
Yeah, Tusha, so could you go back to the architecture? Yeah. So for the attention part, actually there are it will repeat for n time, right? So it means that there are n such structure. So my question is that so for every time we repeat this structure, so are we going to have the same k value for each structure, or will them be different?
K value?
No. So we have the encoder and the decoder here, right? For the encoder, I mean for the decoder part. So we have an such attention structure. So they are sequentially. So for example, for the attention part 1, they have the k value from the encoders. And for the attention part 2, are they going to have the same k value, or the k value will also evolve?
So you're asking like k values for this versus k values for this?
No. So I know for the second one it's the self attention. So for the first one is cross attention. For the actually my question is about the cross attention. For the cross attention, it will this structure will happen for n time, right? For every time, are they going to use the same?
Yeah,
K1, K2,
yeah. They just mentioned in one line, you can use multiple of these in sequence to build the architecture. That's just one line there in the paper, and they've not mentioned anything. So I have to look up into the code how they've implemented it in this. So like because after this you get output sequence similar to this, then the cross attention does not make any sense, because then you again be using these things. I'm not sure if I think what they're doing is again just replacing these queries with this and using this again. Like I have to see what they're doing, if they're doing this again here like this.
Yeah, makes sense. So I think we can check the code for that.
Yeah, because they haven't mentioned in the paper, they haven't mentioned the implementation details, like for the architecture, how it is done.
Yeah. Okay, all right.
So it's like a continuously apply the cross attention, self attention, then cross attention, self attention.
They're saying that repeat these blocks multiple times to build the arc. Just like a one-liner they've mentioned at the end of the section that these can be used in multiple in conjunction to each other to get the good results, like things like that.
Then I guess they have to vary the QKV matrices, right?
Yeah. If they have to use cross attention, then yeah, Q and V has to be different.
Okay. Oh, one thing, if you have so after self cross attention, all the at every query point you got one vector, right? How do you conduct cross attention again? There won't be any cross attention.
Yeah, that's maybe because after this there is only one vector. You don't have.
So the only explanation will be okay. I got after cross attention, self attention, I have eventually I got for every query point I got Q vector again. Then I do the cross attention with the K1, K2, K2, and so on in the bottom block. I do this again.
Yeah. Maybe I think I have to check the code. They haven't mentioned this in text. I have to check the code if they're doing this.
This is the only explanation, right?
Yeah, it should be. Yeah. If they're using multiple cross attentions, then cross attention. If they're only using self attentions after this, then they don't need this. And like if they're only repeating self attention, like if they're only repeating this block after this, then they don't have to use this.
What's your thought, Xin? Xin, what's your thought?
Sorry, I was mute. I was muted. So I didn't. I'm just checking their code. So yeah. So what did Tushar say? Sorry for that.
So I mean, we're talking about how do they repeat this attention block. If they repeatedly doing cross attention, self attention, then cross attention, self attention, the only you have to fix their K1, V1, K2, V2, K3, V3 until KM, VM, right? What you change is just the Q.
Yeah, so I mean, from the architecture, it seems that they always have the same K and V for different queries.
Yeah, because after you're doing this cross attention, you can only collect some vector, some representation for every query point.
Viewpoint, yes, exactly. Yeah.
And you do a bunch of self attention, it doesn't change this fact. And then you can review them as you can retreat them as the query vectors at the query points, and then you do the cross attention again.
Yeah, actually, yeah, that's right. But actually, it doesn't matter. I think for the transformer, one of the attribute for the transformer is that the number of the query is always the same across the whole network, right? And also for the dimension of the query, K and the value, they are always the same. So it's very convenient to compute. No matter how many query you have, or how many K and value you have, they are the same. So I think that's why this can be grade free, because for different PD equation, you can have different number of the queries. That doesn't matter.
Okay. Yeah, Tushar, maybe we can proceed to the results.
Yeah. So these are the results. MIONet, it's like a variation to DeepONet with multiple branches, multiple trunks. So something like that. FNO, this is this standard FNO where you need equispaced grids and all that. This is some Galerkin transformer they mentioned. I don't know the details like how this works. The GeoFNO is just a modification to FNO to support non-uniform grids in this. And O transformer, this is some variation to Galerkin transformer. And then there's G0 in this. So the data set, they used RC2D. And I think this NACA is the what I think what the Michael was discussing in the meeting last time, what they also did for the paper, like what I think you did for your paper also, one of those papers. It's like airfoil experiment, thing like that in this here. So the results that I could see, like the difference if you see from like a standard FNO or even like from like a GeoFNO, the order of magnitude, it's not like a big difference in these results. It's not like it's 2 orders magnitude, or even if you see like this also, it's not even not 1 order magnitude. It's like a half an order better in this. And this is very similar across all methods. If you look at this.
Yeah, and why didn't they report the standard deviation?
Yeah, they haven't. And if you look at it from the DeepONet, again, not a big difference. Very, very similar. Where you see -2, it's like 2 to the power -2. This is 7 -3. Again, -2. Like not a big difference from this.
Yeah, in this case, they should repeat the experiments multiple times to get standard deviation.
Yeah, there is no plus minus at the end, like here. Yeah.
Yeah, it's not hard to get standard deviation at all, right?
Yeah.
That's why they didn't report that. They just pick the best result. Better than.
Yeah. I suspect that. I think if they do this, it will become worse.
Yeah, what else?
Yeah, so these are the results. This is the.
Okay. Yeah, perfect. Yeah, I really like your presentation, Tushar.
Yeah, so it was hard to. I was thinking of doing it in a PPT, but there's so many details, and like I have to read up blogs, I have to read different papers just to condense everything down to something that I could understand. this was the only thing I could find how I can write this down. And even this, I have to look at the implementation to be sure that I'm understanding all the points correctly. Self-attention and all these things, I know this is right because I implemented self-attention, multi-attention. Like personally, I only understand things when I implement them. So self-attention, multi-attention, I implemented from scratch in Python. And this, I know this is right. This is how it works. G0, I have to look into the code, how and figure out how they're doing things and how it is working. This.
Yeah, I think the most point that inspire me, the biggest thing that embarrassed me embarrassed me most is they use this self-attention mechanism to piece different information or different source of information together to align with the query points. I think that's a very interesting idea. But to me, maybe it's because I'm not familiar with attention mechanism. At least when they apply that, it's a good way to merge the information from heterogeneous source together to predict the solution value at different query points. Right?
Yeah, yes.
I think that's a very useful trick or very useful design.
Yeah.
Okay. Any other comment?
So tomorrow I'll present this to Mike also in our meeting shortly, and maybe he'll have some input, because these things where they draw inspiration from domain decomposition and all these things, Mike will have a lot more knowledge about this, like how this, if this makes sense.
No, I mean that domain decomposition interpretation totally makes nonsense. It's just people written trick, and I'm really kind of skeptical how they get in, because their table doesn't have any standard deviation. That's right. That doesn't make any sense, right? Because it's like regression problem. You should be able, like, you split the data set for 5 folds, use 4 folds for training, the remaining 4 for testing, or just random split, do it multiple times. It's very easy.
Yeah.
The data report, there must be some reason on that. I guess their performance is not as good as what they highlighted there.
Yeah, it's very small difference. So if you look at the best performance, it's very small. So if you look at the mean, and it will definitely be very close. Yeah.
But I think the valuable part is still there. Like you can use self-attention mechanism, right, to piece those different sources of information and make prediction.
Yeah.
I mean, it's not necessary to apply the attention block for every component, right? You can use other components as well. But if you want to piece them together, yeah, that cross attention seems a good choice. Any other comment? Okay, I think we are very efficient today. We don't need the second half of the seminar. Let's stop. And again, we won't have seminars in the following 2 weeks because we're going to prepare some submissions to ICR and ALStats. So I will make a notice when we want to resume the seminar. Okay, thanks.
All right, bye. Thank you.
Thank you.